In the late summer of 1859, the Earth seemed unchanged, quiet in its rhythm. Oceans rose and fell in their endless breathing. Gas lamps flickered across cobblestone streets, their glow fragile against the night. Horse-drawn carriages rattled over bridges, while telegraph lines stretched like veins across continents carried the first whispers of an interconnected world. Humanity was beginning to lace the planet with wires of thought and signal, unaware of how fragile those threads truly were. Above, the sun burned in its eternal blaze. To those who looked skyward, it was the familiar giver of warmth and light, steady and faithful. But deep within its roiling surface, magnetic storms twisted like restless serpents, storing an energy vast enough to unmake order on Earth. For the sun is not only creator, but destroyer, a furnace that feeds life, yet harbors the power to scorch it into silence. On September 1st, that duality was revealed. Without warning, the sun expelled a storm so violent it crossed 93 million miles in less than a day. Invisible torrents of plasma struck the Earth's magnetic shield with the fury of a cosmic hammer. Auroras erupted across skies as far south as Havana and Rome, painting the heavens in blood-red curtains and ghostly green veils. Telegraph operators found their instruments alive with fire, their wires spitting sparks, their systems burning without batteries, as if the Earth itself had become an electrical engine. The world had witnessed the Carrington Event, the greatest solar storm ever recorded, and with it arose a question that echoes still. What exactly happened that day? Could it happen again? And if it did, would our fragile world survive? The year was 1859, and the science of the heavens was still a fragile pursuit. The telescope, though centuries old, was only just beginning to peel back the mysteries of the sun. Astronomers gazed into its brilliance through smoked glass and hand-polished lenses, sketching what they saw with pen and ink, for the camera had not yet become a tool of science. The sun appeared to them as a glowing disk, serene from afar, yet pocked with dark, shifting blemishes called sunspots. These sunspots were known but little understood curiosities that seemed to move across the solar face like stains upon perfection. Among those who devoted themselves to the patient study of the sun was Richard Carrington, a wealthy young man in Redhill, England. Astronomy for him was both passion and discipline. He had built his own private observatory, a quiet sanctuary with white-painted walls and heavy brass instruments, where the cosmos could be observed in solitude. Carrington was an amateur, in the sense that he did not earn his living from the stars. Yet he was as meticulous as any professional of his day. His charts were clean, his records precise, his eye disciplined. On the morning of September 1st, 1859, Carrington positioned his telescope toward the solar surface, intending to make his routine observations of sunspots. The day was clear, the air still, and the sun revealed itself sharply against the lens. Before him lay a complex cluster of dark marks, their forms carefully sketched in his notebook. And then, as if the heavens themselves had torn, Carrington saw something no human had recorded before. Two brilliant patches of white light erupted within the cluster. They did not glow softly, but flared suddenly with the intensity of lightning on the solar face. For 5 blinding minutes, these luminous forms expanded and shifted, as though vast fires were raging upon the sun itself. Carrington was stunned. He sketched the event with trembling urgency, capturing the shifting shapes before they faded. And just as abruptly as they had appeared, the lights vanished. Elsewhere in London, another observer bore witness to the same spectacle. Richard Hodgson, working from his own modest observatory, saw the same searing bursts on the solar surface. Two independent witnesses, unconnected, had glimpsed the first recorded white light solar flare, a phenomenon invisible to the naked eye, but powerful enough to scar the Earth. Yet Carrington and Hodgson could not know, in that quiet hour of sketching and wonder, what storm their observations heralded. For even as they recorded their notes, invisible waves of plasma and charged particles were already racing toward Earth, unleashed from the sun with incomprehensible speed. The 19th century was a world only beginning to touch the edges of electricity. The telegraph was the marvel of the age, lines strung across fields and mountains, carrying pulses of current that linked cities and nations. For the first time in human history, words could travel faster than horses, ships, or steam. The world was laced together by fragile wires, humming faintly with electricity, and it was those wires that would become the first victims of the sun's fury. In telegraph offices across Europe and North America, operators felt their instruments tremble. Sparks leapt from the keys, paper caught fire, and men recoiled from shocks that traveled through the very air. Systems that had been disconnected from batteries continued to function as though some unseen power source was coursing through the wires. The current came in so strongly, one operator recalled, that the paper in the office was set on fire. Another reported that even with his batteries unplugged, messages continued to transmit over hundreds of miles, powered by the storm from the sun itself. Night fell, but the heavens did not darken. Across the skies of Havana, Jamaica, and the Mediterranean, the aurora spread ghostly lights usually confined to the Arctic, now spilling into the tropics. Curtains of green, red, and violet shimmered across cities where such skies had never been imagined. In the Rocky Mountains, miners awoke at midnight, thinking dawn had come. So brilliant was the glow of the heavens. The people of 1859 did not understand what they were seeing. To many, the auroras were omens, visions of fire in the sky, or even portents of divine anger. Newspapers recorded astonishment and fear in equal measure. One New Orleans account spoke of blood-red draperies hung across the sky, fringed at the bottom with green. In Boston, crowds gathered in the streets, watching the heavens ripple like curtains set ablaze. And all of it, the fires and the wires, the lights in the night, the awe of the world had begun with the flicker of light Carrington had seen through his telescope that morning. A burst of brilliance that lasted mere minutes upon the sun's surface had set into motion a storm that would sweep across the Earth. What Carrington and Hodgson had observed was only the herald. The true storm was still arriving, and with it, humanity had taken its first glimpse of a truth both beautiful and terrifying. The sun was not a gentle constant, but a restless giant, capable of reaching across the void to shake the very bones of the Earth. This moment, sketched in haste on September 1st, became the birth of heliophysics, the science of the sun's interaction with our planet. It was the first recognition that the star which nourished life could also hurl destruction, and that the space between sun and Earth was not empty, but a battleground of invisible forces. For the men who saw it, the event was bewildering. For the world that felt it, it was unforgettable. And for science, it was the beginning of a story that would unfold for centuries. The story of how the sun, in a single day, revealed both its brilliance and its wrath. The news of strange lights in the sky and fires in the telegraph wires spread quickly through newspapers journals, and letters. In the mid-19th century, the telegraph had been hailed as a miracle of modern progress, proof that humanity was mastering nature with the language of electricity. Yet within days, this proud invention was humbled by forces beyond comprehension. What men had built with copper and iron had been undone by storms that originated 93 million miles away. Reports arrived from every corner of the world. In Paris, operators wrote of instruments clicking wildly without batteries. In Philadelphia, telegraph lines glowed with unearthly currents. From Havana to Santiago, fishermen described crimson skies that reflected upon the sea like fire upon glass. The auroras swept across two hemispheres, lighting regions that had never before known such colors. The heavens seemed alive, bending and writhing as though painted with fire. But while the spectacle astonished common eyes, in the small circles of scientific inquiry, it raised unsettling questions. What power had reached across the void to disturb the earth so violently? And how could the serene light of the sun, symbol of stability, itself harbor such violent potential? Richard Carrington himself struggled with what he had witnessed. His drawing of the flare was meticulous, yet he hesitated to claim its significance. To him, it seemed almost unbelievable that the sudden outburst on the solar surface might be linked to the telegraph chaos and auroral storms that followed. In an age when many still believed space to be an empty void, the idea that eruptions from the sun could travel through that void to strike Earth was both radical and unnerving. The 19th century scientific world was still piecing together the nature of electricity and magnetism. James Clerk Maxwell's great unification of electromagnetic theory was still a few years away. Michael Faraday had only recently demonstrated the invisible lines of force surrounding magnets, sketching arcs of influence that no eye could see. These discoveries hinted that unseen fields permeated the universe, but their reach was not yet fully imagined. Into this landscape of half-understood forces came the Carrington Event, a natural experiment on a planetary scale. Observatories across the globe had been quietly recording the fluctuations of Earth's magnetic field, and on that September day, their instruments went wild. Needles swung violently, ink traces spiked in sudden storms of motion. What had once seemed stable and eternal, Earth's own magnetic shield, was revealed as pliable, vulnerable, shaken by an unseen hand. For many, the event was an unsettling revelation. The sun was not a distant lantern shining passively across the void. It was an active, volatile star, capable of touching Earth directly, capable of reshaping the invisible environment in which life unfolded. The familiar separation between heaven and earth had been breached. The parallel stories of that week formed a tapestry of awakening. On one side, the astronomers with their telescopes, Carrington and Hodgson, capturing with ink and memory the first burst of light ever known as a solar flare. On the other side, the telegraph operators, their hands scorched, their machines possessed by a current they could not control. And above them all, the auroras, ghostly messengers, writing in light what science had not yet found words to explain. This was the dawn of a new understanding, though it would take decades to unfold. In hindsight, the Carrington Event was the first recorded demonstration of what would later be called space weather, the constant flux of charged particles, fields, and radiation that flows between sun and earth. But to those who lived it, it was only a mystery, a terrifying breach of order, a reminder that the world was not insulated from the cosmos, but enmeshed within it. Consider the irony of the moment. Humanity, in 1859, had just begun to master long-distance communication, stretching wires across continents and oceans, shrinking the planet with pulses of electricity. And yet, before the system had matured, the sun itself reached out and seized those same wires, demonstrating that the universe was already wired, that Earth was already connected to the furnace above. The telegraph, the proud symbol of man's conquest of distance, became the first instrument to reveal our vulnerability to the sun. Philosophically, it was as though nature had whispered a warning. Progress built on fragile foundations can be unmade in an instant. The same wires that carried words across continents could be burned by forces beyond imagining. The same skies that promised dawn could ignite with crimson fire. Civilization's first step into electrical modernity was met by a reminder of its fragility. For Carrington and Hodgson, the flare they observed was a scientific curiosity, but its implications would grow with each generation. They had not only documented a flare, they had recorded the first chapter of heliophysics. Their sketches became evidence that solar activity was not mere surface blemish, but a force capable of shaking Earth itself. In the years that followed, scientists began to piece together the puzzle. They correlated sunspot activity with magnetic disturbances. They noted that auroras flared more brightly when solar blemishes were most numerous. Slowly, a picture emerged. The sun was a restless sphere, and its storms traveled outward across space, carrying energy that could bend fields, ignite skies, and set wires aflame. And yet, in 1859, no one could see the full scope of what had occurred. They had no satellites to watch the sun's corona, no instruments to measure the solar wind, no models of magnetospheric storms. They had only their eyes, their pens, and their bewilderment. The Carrington Event stood, then, as both spectacle and omen. The spectacle because it revealed in light and fire the invisible ties between Earth and sun. An omen because it suggested a danger not yet understood, a reminder that the star which gave life could also threaten it. Humanity had glimpsed, for the first time, the storm beneath the light. From the calm of English observatories to the chaos of American telegraph offices, from the miners who mistook midnight for morning to the sailors who watched blood-red skies shimmer upon the seas, the event carried a single lesson. The sun was not merely a background presence. It was a force woven into the fabric of life, capable of violence as sudden as it was vast. The dawn of heliophysics had begun not in quiet theory, but in shock in wires burning, skies igniting, and astonished eyes turned upward. And though Carrington and Hodgson could not know it, their sketches of light upon the sun would become the first lines in a new book of science, a book that is still being written as humanity learns, slowly and uneasily, just how close we live to the fire. When the flare faded from Carrington's lens, silence seemed to return to the sun. But upon the Earth, the silence did not last. Within hours, the planet itself seemed to tremble under an unseen tide. It began as strange fluctuations in magnetic instruments, needles swinging without reason, dials jerking erratically. And then, as if the heavens had opened a conduit to the earth, the storm arrived in full. The skies were the first to betray the scale of what had come. That night, darkness never truly fell. Across the high latitudes of Canada and Scandinavia, auroras erupted in waves of light that cascaded like rivers of fire. Curtains of green and violet shimmered across the vault of the heavens, bending and folding as though the sky itself had been set aflame. But unlike ordinary auroras, which rarely strayed beyond the polar circles, This display spilled deep into latitudes unprepared for such a vision. In Havana, Cuba, witnesses described ghostly sheets of crimson draped across the Caribbean night. In Hawaii, fishermen looked upward in awe, as though volcanoes had erupted not from the sea, but from the sky. Over Rome, scarlet arcs stretched across the ancient dome of heaven, bathing temples and cathedrals alike in blood-colored light. Reports from the American Midwest told of skies so bright that farmers woke at midnight, convinced that dawn had broken. Newspapers in Boston described citizens gathering in the streets at 2 in the morning, reading their papers outdoors under the radiance of auroras. The aurora of September 1859 was not confined to the fringes of the earth. It embraced the globe, spilling light into realms that had never known such colors. It was, by every measure, a storm unlike any in human memory. But the spectacle above was only the beginning. For below, upon the wires that now stitched nations together, the true shock was felt. Telegraph offices across North America and Europe reported chaos. Operators sat at their desks as their instruments came alive, unbidden, clicking wildly with phantom signals. Sparks leapt from the brass keys, scorching hands and igniting papers. In some cases, operators were thrown back in their chairs by shocks that jolted through the very air. And then, an even stranger thing occurred. Telegraph systems disconnected from their batteries continued to function. Messages were transmitted across hundreds of miles without any source of power. The storm from the sun itself had become their engine, driving currents through wires as though Earth had been seized by an alien grid. The current came in so strongly, one operator wrote, that the paper caught fire. Another noted that after unplugging his system from its batteries, communication went on better without them. For a society that had only just begun to understand the power of electricity, the event was both wondrous and terrifying. To the common observer, it seemed as though the Earth itself had become a living machine, its veins coursing with fire from the heavens. To scientists, the phenomenon was an enigma that defied explanation. How could the sun, distant, serene in the sky, suddenly hurl such invisible violence across 93 million miles? At the time, the prevailing view of the sun was one of stability. It was regarded as a constant furnace, radiating light in steady measure, its cycles slow and predictable. The very idea of civilization rested upon that constancy. Crops grew in its warmth, seasons followed its rise and fall. Life itself was sustained by its energy. But now, with wires burning and skies igniting, that assumption was shaken. The sun was no longer simply the provider. It had revealed itself as something else, a force capable of violence on a planetary scale. This realization struck at the foundations of scientific thought in the mid-19th century. Electricity and magnetism were still being explored, their principles debated and refined. Faraday had only recently mapped invisible fields with lines of iron filings. Maxwell had not yet completed his equations uniting electricity, magnetism, and light. The cosmos was still imagined by many as a clockwork of predictable, stable motions. And now, suddenly, here was proof that a star could lash out with ferocity, shaking the very bones of the Earth. For those who witnessed it, the shock was not merely scientific, but existential. If the sun could reach across space and burn the veins of technology, what else might it do? Could it extinguish the telegraph entirely? Could it set the world ablaze? To a civilization just beginning to taste the fruits of electrical power, The Carrington Event was both revelation and warning. The newspapers captured the mixture of awe and dread. In New Orleans, one report described blood-red draperies hung across the sky, fringed at the bottom with green. In Boston, crowds marveled at the midnight glow, their faces lit as though by a phantom sunrise. In San Francisco, miners wrote home to families, describing how the night was so bright they could read their letters beneath the stars. Across the globe, astonishment mingled with fear. Was this an omen? A sign of divine displeasure? Or a natural wonder beyond understanding? For the scientific community, the event posed a more unsettling challenge. If the sun could do this once, could it do so again? And if so, what might be the consequences for a world growing ever more dependent on fragile networks of wires and currents? The Carrington Event forced a reimagining of the sun. It was no longer a passive sphere of light, but a restless furnace capable of sending storms that could engulf the Earth in both beauty and terror. It was in every sense a scientific shock, a revelation that the universe was not as stable as it had seemed, and that humanity's new machines of communication were vulnerable to powers far beyond their control. And so, in September 1859, the world learned a truth that it has never forgotten, though it often prefers to ignore: that our civilization lives not in isolation, but in the shadow of a star whose moods can shape our destiny. The telegraph fires and the auroral storms had already shaken ordinary citizens, but within the halls of science, the implications cut even deeper. To physicists and natural philosophers of the mid-19th century, the universe was supposed to be orderly, comprehensible, a grand machine wound by divine or natural law. Celestial bodies moved in elegant predictability. Light traveled in straight lines. The sun, though mysterious in its inner workings, was imagined as a steady source of warmth. Yet the Carrington Event had torn a hole through this reassuring fabric. At magnetic observatories in Greenwich, Bombay, and Washington, sensitive instruments recorded swings of unprecedented violence. The inked traces on rotating drums jerked into wild excursions, as if the Earth's magnetic field itself had been seized by invisible hands. What had always seemed a slow, gentle compass of the planet now revealed itself to be vulnerable, pliable to forces no one could yet measure. The quiet hum of natural order had given way to a roar captured not by human ears, but by quivering needles and scorched telegraph keys. The contradiction gnawed at scientists. How could a burst of light seen by Carrington and Hodgson be connected to disturbances felt on the ground? The vacuum of space was assumed to be empty. How then could violence travel through nothingness? The very idea strained belief. Some suggested a form of radiant electricity. Others speculated about mysterious ethers that might carry influence across the void. None could yet grasp that a river of charged particles flowed constantly from the sun, that the Earth itself sailed within a stormy sea of plasma. For the public, the experience blurred into myth and omen. Some communities saw the crimson auroras as heavenly warnings, echoes of biblical fire. Ministers preached sermons linking the storm to divine wrath, urging repentance. In rural villages, where news of Carrington's flare would not reach for decades, the aurora remained a supernatural visitation, a wonder and a terror never forgotten. For the learned classes, however, the event was both a challenge and an invitation, proof that the universe was more volatile than presumed, and that humanity had only just begun to scratch at its deeper forces. In that sense, the Carrington Event was a rupture not only of wires and skies, but of confidence. The 19th century was an era of triumphalist science, a time when many believed all mysteries were destined to yield before the rational gaze. Diseases were being traced to microbes, chemistry was systematizing elements, geology was measuring the age of Earth itself. In this march of progress, the sun seemed a solved question, a celestial furnace, distant, dependable. But the storm revealed an unruly side, a reminder that beneath apparent constancy, chaos could erupt without warning. The shock was sharpened by contrast. Civilization had just begun to weave its first fragile network of electricity, and already it had been undone by forces no engineer could master. The telegraph, a triumph of control, was turned into a conduit for chaos. The message was stark. Progress did not shield humanity from nature, it tethered humanity more tightly to it. The very inventions that symbolized mastery also revealed vulnerability. Philosophically, the event whispered of a universe where order and violence were intertwined. The same star that gave life to fields and oceans had shown its power to hurl destruction. The boundary between benefactor and threat blurred. To stand beneath the aurora of 1859 was to feel awe and fragility at once, to realize that the world, solid underfoot, was suspended in an environment both nourishing and hostile. Scientists continued their debates. Some argued that sunspots were the cause, noting the coincidence between the massive clusters Carrington had drawn and the storm's arrival. Others resisted, uncomfortable with the notion that something so distant could wield such power. The understanding of magnetism and electricity was too new, too incomplete to provide clear answers. But slowly, a seed had been planted, the recognition that the sun and earth were not separate, but bound by invisible currents, partners in a cosmic exchange both beautiful and dangerous. The Carrington Event thus became more than a natural occurrence, it became a turning point. It suggested that the sun was not passive, but active, not constant, but restless. The Earth, once imagined as an isolated stage for human endeavor, was shown to be woven into a wider theater of cosmic forces. The event's true science would take generations to unravel, but the shock of its revelation was immediate. And perhaps the most unsettling realization was this. The storm had left little lasting damage only because the world of 1859 was still simple. Telegraph lines burned, yes, and operators were shocked, but life continued. Farmers still plowed, ships still sailed, cities still glowed with gaslight. The storm was terrifying, but survivable. Yet even in that moment, some foresaw a darker possibility. What if the storm returned in an age when all of civilization ran upon wires? What if the sun's violence struck a world utterly dependent on fragile currents? The question lingered like a shadow. For if the sun could, in a single day, ignite skies across the tropics and turn telegraphs into fire, then what might it do to a world of satellites and grids? In the weeks that followed the storm of September 1859, the world slowly returned to routine. Telegraph lines were repaired, auroras faded back toward the poles, and the skies resumed their ordinary hues. To most, it was only a strange episode, a night remembered for its lights, a week remembered for its fiery wires. But within the quiet chambers of observatories and across the pages of scientific correspondence, something deeper was stirring. A mystery had been revealed, and it demanded investigation. The Carrington Event had left behind more than memories. Around the world, magnetic observatories, small, scattered institutions devoted to the subtle measurements of Earth's geomagnetic field, had captured its fury with mechanical precision. At Greenwich in London, The magnetometers had recorded violent swings, their traces leaping across paper drums. In Bombay, the same wild fluctuations had been inscribed, thousands of miles away, yet synchronous in their rhythm. Washington's observatory told the same tale. The evidence was undeniable. The Earth's magnetic shield, usually a slow and steady guide for compasses, had been struck with force enough to send it reeling. Scientists began to compare notes. The coincidence between Carrington's flare and the geomagnetic storm was too striking to ignore. Could it be that the sudden burst of light he had sketched was connected to the disturbances felt across the globe? The question was radical, for it implied that the sun could project its violence across the empty void of space, altering the very environment of the Earth. The tools of the era were crude by modern standards. There were no satellites to watch the sun's corona, no spacecraft to measure the solar wind, no radio telescopes to catch the whispers of electromagnetic storms. Instead, there were compasses, inked charts, telescopes fitted with smoked glass, and the patient eyes of observers. Yet from these simple tools, a pattern began to emerge. Sunspots, those dark blemishes that drifted across the sun's face, had long puzzled astronomers. Galileo himself had sketched them centuries earlier, noting their shifting forms. By the 19th century, they were recognized as real features upon the sun, not mere shadows or planets transiting its disk. Their periodic increase and decrease had even been charted, suggesting a hidden cycle within the solar furnace. But the Carrington Event forced scientists to reconsider their significance. Were these spots not merely curiosities, but the visible scars of deep magnetic storms? In the aftermath, correspondences between European and American scientists grew urgent. They noted that the geomagnetic storm coincided with a particularly large and complex sunspot group, the very one Carrington and Hodgson had been observing. Reports linked the timing of solar disturbances to auroras and compass irregularities. It was as though the Earth's invisible environment, its magnetic cocoon, was tied to the temper of the sun. Still, the mechanism was beyond their grasp. How could the sun's eruptions, observed as sudden flares, send their influence across 93 million miles of emptiness? Some imagined electrical currents flowing through the ether. Others suggested streams of matter hurled outward, though such notions seemed extravagant. Theories wavered between poetic speculation and careful measurement. Yet a new field of inquiry had been born. This was the dawn of what would one day be called heliophysics, the study of the dynamic relationship between sun and earth. In 1859, it had no name, no structure, only the urgency of a great question. But every flicker of aurora, every tremor of the compass, every dark blot upon the solar face now seemed charged with meaning. At the same time, governments and institutions began to see the practical necessity of such study. Telegraph systems. The arteries of communication had proven vulnerable. Commerce, diplomacy, and even security had felt the sun's touch. If storms from space could disrupt the fragile lattice of wires, then understanding their cause was no longer an idle pursuit, it was essential. Across Europe, new magnetometers were installed, observatories expanded their programs, and networks of observation were quietly knit together. In America, the Smithsonian Institution began to advocate for systematic geomagnetic monitoring. The Carrington Event had awakened a realization that Earth was not isolated, but linked to its star in ways both wondrous and dangerous. In the cultural imagination, too, the storm lingered. Writers and poets evoked the auroras as symbols of celestial fire. Farmers spoke of the night when morning came twice. Mariners recalled seas bathed in an eerie crimson glow. But beneath the poetry lay a gnawing unease. If such a storm could arrive without warning, what might await in the future? Was the Earth always at the mercy of the sun's hidden tempests? The deeper investigation was thus not only scientific, but philosophical. Humanity had always revered the sun as a giver of life, but now it was revealed as something more complicated. A being of moods, a furnace with tempests. The line between benefactor and destroyer blurred. To study the sun was no longer only to measure its steady cycles, but to probe its storms, to anticipate its anger. For Carrington himself, the aftermath was bittersweet. Though his observation would immortalize his name, he was not celebrated in his time as a discoverer of cosmic truths. His flair was regarded with caution, even skepticism, by those unwilling to link it to earthly chaos. Only later would his sketches be recognized as the first record of a solar flare, the visible spark of a storm that had encompassed the globe. And so, in the wake of 1859, science stood at a threshold. The mystery had been revealed, but not explained. The tools were too few, the theories too untested. Yet the seed had been planted. The realization that the Earth's environment was not its own, but part of a vast and restless system ruled by the sun. What had begun with sparks in telegraph wires was now becoming something greater. The first steps toward understanding the invisible storms of space. The aftermath of the Carrington Event lingered like an unanswered question. Though the auroras had dimmed and the telegraph lines repaired, the event continued to echo across scientific circles. It was too extraordinary to dismiss, too global in scope to treat as coincidence. What had happened in 1859 was not merely spectacle. It was data rare, precious, and demanding to be understood. Scientists began to pore over the records. Observatories had captured the event in ink and steel. Magnetometer traces that jerked wildly, compasses that spun unpredictably, auroral sightings marked carefully in logbooks. When these fragments were compared, a pattern emerged. The disturbances began almost simultaneously across continents, their intensity correlating with the sudden flare that Carrington had recorded. The connection between solar activity and geomagnetic storms, once a matter of speculation, was becoming undeniable. But if the connection was real, what was the mechanism? This question haunted the thinkers of the age. Michael Faraday's experiments with induction had already shown that changing magnetic fields could produce electrical currents. Could the Earth itself, wrapped in its invisible magnetic cloak, be vulnerable to disturbances from beyond? If so, then perhaps the solar outburst had perturbed that cloak, inducing currents in telegraph wires stretched across landscapes. The pieces fit imperfectly, but they suggested a tantalizing framework, that the Earth and Sun were linked not only by light and warmth, but by invisible forces coursing through space. Sunspot cycles became a focal point of study. For decades, observers had noted that the number of sunspots rose and fell in roughly 11-year rhythms. Some dismiss the pattern as trivial, others as coincidence. But the Carrington Event gave the cycle new weight. If the sun's storms aligned with its cycles of spots, then perhaps there was a predictive element. Perhaps Earth's own disturbances could be anticipated by watching the blemishes on the sun's face. Astronomers in Zurich, Paris, and London began to record the spots with greater diligence, comparing their counts to auroral displays and compass records. Slowly, the sun's hidden rhythm revealed itself, its magnetic heart beating in cycles that could sweep across the solar system. Even so, the language of the time struggled to explain what was truly happening. Without the concept of the solar wind, Without plasma physics or spacecraft to confirm their guesses, scientists spoke of luminous matter hurled through space or mysterious ethers carrying disturbances. They imagined currents flowing invisibly across the void, threads connecting sun and earth. Their words were speculative, their theories often flawed, but beneath them lay the seed of truth. Some, however, resisted the implications. The idea that the sun could reach across millions of miles to shake the earth seemed fantastical, even heretical to the neat order of Victorian science. Space was supposed to be a vacuum, a nothingness, incapable of transmitting force. To suggest otherwise was to open the door to chaos, to admit that the void was not empty, but alive with unseen storms. And yet the evidence grew too strong to ignore. With each flare observed, with each compass tremor recorded, the suspicion deepened. The sun was not serene, it was restless, and its restlessness mattered. For practical men, especially those in industry and government, the implications were equally unsettling. The telegraph had proven vulnerable, and it was only the beginning of humanity's reliance on electrical infrastructure. If such storms could strike again, what might they do to future systems? Could commerce grind to a halt? Militaries be blinded? Governments paralyzed? These questions were whispered more than spoken, for they carried an air of dread. But the Carrington Event had made them unavoidable. Thus began the first attempts at coordinated monitoring. Networks of observatories were encouraged to share data, to compare their magnetic records and oral sightings. By the late 19th century, efforts emerged to standardize observations of both geomagnetism and solar activity. A primitive form of space weather science was being born, not yet named, not yet understood, but alive. And within this pursuit lay something more than practical necessity. There was a philosophical shift, a dawning awareness that the Earth's environment was not limited to its oceans, mountains, and atmosphere. It extended outward into a realm shaped by its star. The sun was not merely a backdrop, but a partner, sometimes benign, sometimes violent, in the unfolding drama of life. To investigate it was to recognize that humanity lived not apart from the cosmos, but within it. Carrington himself faded from the center of the story. Though his name would one day be immortalized, his own career did not soar. He remained a private man, more interested in patient observation than in public recognition. Yet the sketch he had drawn, that sudden flare of white light upon the solar surface, became the first piece of evidence in a science that would take more than a century to mature. His moment of astonishment had captured a truth the world was only beginning to see. In hindsight, the deeper investigation begun in 1859 was the birth of a new kind of astronomy. Not the astronomy of distant stars or planetary orbits, but of interactions, of relationships, of invisible exchanges between sun and earth. It was the recognition that the cosmos was not static, but dynamic, alive with forces that could cross the gulf of space in hours, shaping human lives in ways both subtle and catastrophic. The Carrington Event became a reference point, a reminder written into scientific memory that what happens upon the sun does not remain upon the sun. It travels, it touches, it transforms. The storm of 1859 had been an introduction, a dramatic opening act in a science still in its infancy. The investigation that followed was halting, uncertain, but relentless. For once the sun had revealed its violence, humanity could never again pretend it was safe to ignore. And so, out of fire in the skies and sparks in the wires, heliophysics was born, a science of storms, of fields, of the restless bond between Earth and star. It began with confusion and awe, with theories unsteady and incomplete. But it carried within it a promise that one day humanity might not only marvel at the auroras, but understand the storms that wrote them across the sky. The Carrington Event did not fade into obscurity. It lingered, not only in memory and in journals, but in the slow accumulation of evidence that followed. As decades passed, as the science of electricity matured, and as instruments became more refined, the true scale of what had happened in 1859 began to reveal itself. And with each new layer of understanding, the mystery grew darker, deeper, more unsettling. In modern terms, what struck Earth was not simply a flare of light, but a coronal mass ejection, a vast eruption of plasma hurled outward from the sun's surface. To imagine its scale, one must picture 1 billion tons of charged particles, threaded with magnetic fields, released in an instant and cast into the void of space. Most such ejections take several days to reach Earth, carried along by the solar wind. But the storm of 1859 was different. It arrived in just 17 hours, racing across 93 million miles with astonishing velocity. It was, in essence, the fastest solar storm ever recorded. What could account for such speed? Modern heliophysics suggests that the Carrington Event may have been preceded by a smaller eruption, one that cleared the path of slower-moving solar wind, leaving a rarefied corridor through which the second, larger blast could travel unimpeded. Like a cannonball following through smoke, the great coronal mass ejection surged forward with devastating force. When it struck the Earth's magnetic shield, it compressed it violently, sending shockwaves through the magnetosphere, rattling the planet's defenses to their core. The numbers are staggering. Estimates suggest that the storm's magnetic strength may have reached double or even triple that of any geomagnetic event measured in the modern era. Auroral currents circled the planet with immense intensity, inducing voltages in wires, in rails, even in the ground itself. The Earth had been, for a brief time, caught in the grip of a star's unleashed fury. And yet, the true escalation of the mystery lies not in what happened then, but in what might happen if such an event were to occur now. In 1859, the world's reliance on electricity was minimal. The telegraph was a marvel, but it was only a fragile web stretched across a handful of continents. Gas lamps still lit the streets. Horses still pulled carts. Sails still carried ships across oceans. The world was vulnerable, but it was not yet wired into a fragile global network. Today, the picture is different. Our civilization hums with electricity. Power grids span nations. Satellites orbit above. Aircraft crisscross the skies. Undersea cables lace continents together. Every heartbeat of our modern world is synchronized by currents, by invisible pulses of electrons moving through fragile circuits. Were a storm of Carrington's magnitude to arrive now, it would not ignite only telegraph wires. It could cripple satellites, blind GPS systems, melt transformers in power grids, and plunge entire regions into darkness. The auroras would be beautiful, but beneath them, cities might go silent. This realization has deepened the sense of awe and dread surrounding the Carrington Event. It was not merely a historical curiosity. It was a warning, written in fire across the skies, a glimpse of what the sun is capable of. Modern simulations suggest that a storm of similar magnitude today could cause trillions of dollars in damage, disrupt communications for months, and render entire infrastructures useless. Humanity, more connected than ever before, is also more vulnerable than ever to the moods of its star. And yet, the mystery deepens further still. The Carrington Event was vast, yes, But was it the greatest storm the sun has ever produced? Ice cores taken from Greenland and Antarctica hint at even larger solar events in the distant past, their chemical signatures suggesting that the sun has, at times, unleashed storms of terrifying magnitude, far exceeding 1859. These superstorms may occur only once in a millennium, but their possibility lingers like a shadow. If 1859 was devastating to telegraphs, to confront this question is to confront the fragile foundations of civilization itself. For all our advancements, our spacecraft, our satellites, our data streaming invisibly across oceans, we remain tethered to the sun. We are children of its warmth, yet also captives of its storms. The Carrington Event was a reminder that this tether can become a whip, striking without warning, its lash capable of unraveling centuries of progress in a single night. And so the story of 1859 does not end with telegraph fires or crimson skies. It continues, rippling outward into the present, a question that grows sharper with each decade of reliance upon fragile systems. What exactly is the sun capable of? How often does it unleash such storms? And most pressing of all, will it happen again in our time? The deeper scientists dig, the more unsettling the picture becomes. Our star, steady in its light, hides tempests of unimaginable power. The Carrington Event was one such revelation, but it was not unique. Others have followed lesser storms, but reminders all the same that the sun has not finished with us. Each flare, each eruption, each ripple in the aurora carries with it the echo of 1859, a whisper of the day when the sun nearly brought civilization to its knees. This is the escalation of the mystery, the realization that what was once thought rare may not be rare at all, that the sun, in its silence, may be waiting, that the storm of 1859 was not the end, but the beginning of our understanding and the beginning of our fear. The Carrington Event remained, for over a century, a singular reference point, the day when the sun had touched Earth with fire. But as science advanced into the 20th and 21st centuries, evidence emerged that suggested something even more unsettling. That 1859 may not have been the most violent storm the sun has ever produced. It was only the first that humanity, wired and watching, had recorded. In the 1980s, scientists studying ice cores from Greenland and Antarctica discovered unusual spikes of isotopes such as beryllium-10 and carbon-14. These isotopes form when high-energy particles from the sun collide with Earth's atmosphere. Their presence, frozen into ancient ice, revealed that in the years 774 and 993 CE, Earth had been struck by solar events far more intense than anything in recorded history. The spikes were so sharp, so sudden, that they implied storms dwarfing the Carrington Event. Medieval chronicles mention strange red skies, but the science of the storms was lost to time. Only the ice, layered year by year, remembered. These discoveries suggested a chilling truth. The sun has moods far darker than even Carrington witnessed. The storm of 1859 was catastrophic for its time, but in cosmic perspective, it may have been ordinary, a moderate example of what the sun can do when truly angered. Such storms, though rare, remind us that the Carrington Event is not a ceiling, but a threshold. The suspicion deepened further in July 2012. Satellites orbiting the sun, particularly NASA's Solar Terrestrial Relations Observatory, STEREO, recorded a massive coronal mass ejection blasting into space. Its speed and scale were extraordinary, rivaling or even exceeding the storm of 1859. For days, scientists traced its path with mounting alarm, and then came the revelation. Earth had missed the storm by just 9 days. Had the planet been slightly ahead in its orbit, the 2012 event would have struck us head-on. In the words of one NASA scientist, it was a cosmic bullet dodged. The implications were staggering. Modern simulations suggested that if the 2012 storm had struck Earth, it could have caused damage measured in trillions of dollars. Power grids might have failed on continental scales. Satellites could have been disabled. Communication networks crippled. Air travel would have been disrupted, and undersea cables, the hidden veins of the internet, might have burned under induced currents. Recovery, some estimated, could have taken months or even years. The question then is not if, but when. Solar cycles rise and fall every 11 years, with peaks of activity marked by clusters of sunspots and frequent flares. Each cycle carries with it the possibility of a great storm. Statistically, storms of Carrington magnitude may strike once every few centuries, but history has shown that the sun is capable of surprises. The quiet skies of today may conceal the seeds of tomorrow's tempest. Philosophically, the deepening of this mystery touches something primal. Humanity has always looked to the sun as a symbol of permanence. It rises each morning, unchanging in its rhythm, the great clock of nature itself. Yet beneath its steady face lies turbulence beyond imagining. Magnetic fields twisting, reconnecting, exploding. To glimpse the truth is to realize that stability is an illusion. Our star is not serene, but seething. Its light may nurture, but its storms remind us of our fragility. This duality gives the Carrington Event its enduring power as a story. It was not merely a scientific anomaly, but a revelation of cosmic truth, that we live not in isolation, but under constant negotiation with a star that can, without warning, transform the fabric of life. The auroras of 1859 were not only beautiful, they were a warning written in light, a message from the sun itself. And yet, even now, we cannot predict such storms with certainty. Satellites watch the sun, tracking sunspots, measuring magnetic fields, probing the corona with instruments like NASA's Parker Solar Probe. But forewarning is measured in hours, not days. At best, humanity might know that a storm is on its way with enough time to shut down vulnerable systems, to unplug, to shield. But a storm like 1859, fast, violent, unstoppable, would leave little time for preparation. Thus, the mystery deepens into dread. The sun, which has shaped every dawn and every harvest, which guided sailors by its path and poets by its light, carries within it the power to silence our machines, to erase the invisible networks upon which civilization depends. The Carrington Event revealed this possibility once. History, ice cores, and near misses remind us that it will happen again. The escalation is therefore not merely scientific, but existential. Humanity has always balanced between awe and fear before the sun. In temples and myths, it was worshipped as god and destroyer alike. In science, it became a star, vast but calculable. But the Carrington Event tore away both myth and certainty, leaving a raw truth. The sun is both gift and threat, and somewhere within that paradox lies our future. For the storm of 1859 was not an ending, but an omen. The true question is no longer what happened that day, but what will happen the next time the sun decides to remind us of its power. The Carrington Event left behind questions that the 19th century could not fully answer. Observers had seen the flares, operators had felt the shocks, and instruments had recorded the magnetic storms. But the mechanism, the hidden architecture behind the chaos, remained elusive. As decades passed, new tools, new theories, and new imaginations began to circle around the mystery. What exactly had the sun unleashed in 1859? The first line of speculation arose from the link between sunspots and geomagnetic storms. By the late 19th century, astronomers had firmly established that sunspots were not illusions or passing planets, but real phenomena upon the solar surface. They darkened the sun's face in complex patterns, shifting and twisting with invisible energy. The Carrington Event coincided with an enormous sunspot group, so vast it could be seen without a telescope through smoked glass. Could these dark marks be the birthplaces of storms? The idea gained momentum. Sunspots seemed to cluster during times of heightened auroras, and geomagnetic disturbances echoed their cycles. If spots were scars of magnetic turmoil within the sun, then perhaps their eruptions reached across space to strike Earth. The notion was radical, yet it fit the evidence. Carrington had drawn the flare within such a cluster, and hours later, the Earth itself had trembled. Still, the mechanism remained hidden. Scientists spoke of luminous matter hurled outward, or waves of electrical fluid streaming through the ether. The vacuum of space was imagined as a subtle medium, a kind of invisible fabric that could transmit disturbances. This ether became the placeholder for forces not yet understood, a bridge between the observed flare and the fires in the wires. With the turn of the 20th century came new clarity. Advances in electromagnetism, Faraday's induction, Maxwell's equations provided a language for unseen connections. The Earth was no longer imagined as isolated, but as wrapped in fields, invisible geometries that could be bent and shaken. If the sun too possessed such fields, then eruptions upon its surface might project disturbances across the void. The Carrington Event became, in hindsight, the first evidence of what would later be called space weather. By the mid-20th century, the picture sharpened again. Rockets and satellites ventured beyond the atmosphere, carrying instruments capable of measuring the streams of charged particles flowing from the sun. This constant outflow became known as the solar wind, a ceaseless gale of protons and electrons, sculpting the Earth's magnetic shield, stretching it into a tail, pressing it into a shield. The Carrington Event, now reinterpreted, had been a titanic blast within this wind, a coronal mass ejection, hurling plasma threaded with magnetic fields at extraordinary speed. This discovery reframed the mystery. The sun was no longer a steady lamp, but a dynamic engine of magnetic storms. Its corona, shimmering faintly around eclipse disks, was not empty light, but the birthplace of eruptions capable of swallowing planets. Carrington and Hodgson had seen the visible flare. The Earth had felt the arrival of the invisible storm. The two were bound as cause and effect, though separated by the void. Speculations multiplied. Some wondered whether the sun might be capable not only of storms like 1859, but of events far larger, solar superstorms. Ice cores and tree rings hinted at spikes of isotopes, markers of past bombardments by solar particles. If so, then the Carrington Event was not an outlier, but a reminder of what the sun routinely does across millennia. Could it, in a single burst, reset the stage of civilization? Others reached further still. If the sun could unleash storms, could stars beyond it do the same? The discovery of stellar superflares on sun-like stars, eruptions hundreds of times more powerful than Carrington's, opened new horizons of speculation. Was the sun capable of such violence, given the right conditions? Or was it gentler than its cousins? restrained by cycles we barely understood. Within these speculations lay the deeper philosophical tension. The Carrington Event had shown humanity that the sun is not constant, but restless. But how restless? How dangerous? To answer was to confront by the 21st century, the conversation deepened into urgency. In 2012, as satellites recorded a storm that narrowly missed Earth, scientists revisited Carrington's legacy. The speculation sharpened. Are we prepared? Could we endure a recurrence? Models suggested that modern society, woven together by fragile electronics, might suffer damage beyond imagining. Unlike 1859, when only telegraph wires had burned, a future Carrington event might silence the satellites that guide airplanes, the grids that power cities, the cables that knit continents. The theories, then, are not idle curiosities, but urgent speculations. They stretch from sunspot cycles to plasma physics, from solar winds to multiverse-scale questions of stellar behavior. They are united by one haunting truth: the sun is more complex, more volatile, more capable of surprise than we once believed. And within that truth lies the deepening mystery of 1859. The Carrington Event was not merely a past storm. It was a window, a glimpse through which humanity first saw the storm beneath the light. The theories and speculations that followed have not closed the question, but opened it wider. For the more we learn, the more we realize how much remains hidden, how much the sun still conceals within its fire. The search for answers to the Carrington Event did not end with the discovery of solar wind. If anything, it only sharpened the mystery. Scientists now knew that vast eruptions of plasma and magnetic fields could hurl across space, yet the details remained elusive. How exactly do such storms begin? Why do some flares remain small, while others swell into planetary threats? And what combination of forces produced the unparalleled storm of 1859? One school of thought pointed to magnetohydrodynamics, the physics of charged fluids threaded with magnetic fields. Within the sun, boiling plasma rises and falls, twisting magnetic lines into knots. These knots can snap and reconnect in sudden bursts, releasing energy equivalent to billions of nuclear bombs. In this model, Carrington's flare was the visible spark of such a reconnection, while the accompanying coronal mass ejection was the true storm. A colossal bubble of magnetic plasma hurled outward. But why so fast? Why so violent? Some researchers suggest the 1859 event was not a single eruption, but a sequence. A smaller CME may have cleared the path of slower solar wind, reducing drag in the interplanetary medium. The second, larger CME then rode this cleared channel like a stone skipping across smooth water, arriving in less than 18 hours. This double strike hypothesis explains both the speed and the extraordinary impact. Others argue that Carrington witnessed a perfect alignment of magnetic fields. The sun's expelled plasma, threaded with its own magnetic geometry, may have collided with Earth's magnetosphere at just the right angle to maximize reconnection. The two magnetic systems, solar and terrestrial, interlocked like gears, transferring vast amounts of energy in moments. The result: auroras at the tropics, telegraphs ablaze, and compasses gone wild. Speculations extend beyond 1859. Could such conditions align again? And if so, how often? Statistical studies of solar storms across the past century suggest that Carrington-level events may occur once every few hundred years. Yet the isotope evidence from ice cores and the near miss of 2012 imply they may be less rare than we hope. Humanity may not be waiting centuries, but merely decades. From here, speculation grows darker. Some theorists speak of solar kill shots, storms so immense they could cripple satellites beyond repair, erode the ozone layer with surges of radiation, or induce currents strong enough to melt vast swaths of infrastructure. Though such scenarios remain extreme, they underline a sobering point. The sun is the most powerful natural force in our environment, and its limits remain unknown. There are even broader speculations reaching beyond our star. Astronomers observing distant sun-like stars have recorded superflares, eruptions hundreds of times more powerful than Carrington's storm. If stars akin to our sun can produce such violence, then is our sun immune? Or has it merely not revealed its full range within the brief span of human observation? A superflare upon the sun would be catastrophic beyond imagination, flooding Earth with radiation, overwhelming satellites, and perhaps stripping away parts of the upper atmosphere. For now, such events seem rare, perhaps restrained by the sun's relatively calm magnetic cycles. But the possibility hovers, a reminder of the scale of stellar power. Even within more grounded theories, uncertainty persists. The physics of magnetic reconnection remains a frontier of plasma research. Computer models can simulate eruptions, but the sun resists full prediction. The Carrington Event thus remains both a benchmark and a mystery, a real occurrence, documented and undeniable, yet still not entirely explained. Speculation also extends to recurrence. What would a modern Carrington look like? Studies conducted by NASA, NOAA, and global power authorities suggest sobering outcomes. A storm of equal strength today could disable a significant fraction of satellites, collapse regional power grids, disrupt aviation, and compromise undersea cables. Economic losses could climb into the trillions, and recovery could take years. Unlike 1859, when society was only lightly touched by electricity, today, every heartbeat of civilization, finance, navigation, communication runs upon currents vulnerable to the sun. And so, within the theories lies a philosophical echo. The Carrington Event forces humanity to confront its dependency. We are a species that believes it has mastered nature, yet we remain tethered to a star that can undo us with a gesture. Each flare we study, each CME we track, carries with it the memory of 1859, the warning that our technologies are but fragile webs before the winds of the sun. Speculation, then, is not idle curiosity. It is preparation, a way of peering into the storm before it arrives. The theories of magnetohydrodynamics, of sequential CMEs, of magnetic reconnection and stellar superflares, all are attempts to understand the hidden architecture of solar wrath. Yet behind them all lingers the same haunting truth. The sun is capable of more than we know, and perhaps more than we dare to imagine. The Carrington Event, seen through the lens of theory, is no longer a solitary episode of the past. It is a glimpse into the future, into storms that may come again, into mysteries still concealed in the restless heart of our star. And until those mysteries are unraveled, we live in suspense, knowing that our sun, in its brilliance, may one day remind us once more of the storm beneath the light. Foremost among these guardians is SOHO, the Solar and Heliospheric Observatory. Launched in 1995, SOHO has circled the sun from its vantage point at the L1 Lagrange point, a stable pocket of gravity where it can watch the solar disk without interruption. Its instruments capture the corona in stunning detail, recording eruptions as they unfold. SOHO's coronagraphs, which artificially eclipse the sun's glare, have revealed thousands of coronal mass ejections, tracing their birth, their arcs, and their velocity. For the first time in history, humanity can watch storms in their infancy, hours before they surge outward into space. Complementing SOHO is the Solar Dynamics Observatory, SDO, launched in 2010. While SOHO gazes outward, SDO stares inward with unprecedented clarity, imaging the sun's surface and atmosphere across multiple wavelengths. Every 12 seconds, it returns high-resolution portraits of magnetic storms unfurling on the solar face. Flares, once fleeting glimpses sketched in haste, are now seen in real time. Their growth and decay traced across ultraviolet and X-ray bands invisible to human eyes. Through SDO, the sun is no longer a distant mystery, but a dynamic canvas of motion, its storms painted in radiant arcs of plasma. Still closer to the fire flies the Parker Solar Probe, launched in 2018. Unlike its predecessors, Parker does not merely observe from afar. It plunges into the corona itself, skimming closer to the sun than any spacecraft before it. Shielded by a carbon composite heat shield, Parker endures temperatures of nearly 1400 degrees Celsius, sampling particles and fields directly within the solar wind. Its instruments taste the charged plasma, measure its velocities, and record the tangled magnetic geometries at their source. Each orbit brings it nearer, until by the end of its mission, it will graze within 6 million kilometers of the solar surface. Parker is humanity's emissary into the storm itself, a machine built to ask the sun the questions Carrington could not. Beyond Parker, a network of satellites and probes watches from multiple perspectives. The Stereo mission, twin spacecraft launched in 2006, offered humanity its first stereoscopic view of the sun, capturing eruptions from different angles. Where Carrington saw a single burst of light, Stereo traced eruptions in 3 dimensions, revealing how they twist and expand as they travel through space. Together, these missions form a vigilant fleet, an armada arrayed against the storms of our star. Yet, spacecraft are only half the arsenal. On Earth, magnetic observatories dot the globe, quietly recording fluctuations in the geomagnetic field. Their needles twitch with every ripple of solar wind, their data streamed to forecasting centers that analyze the patterns. Networks of radio telescopes, too, listen for the sudden bursts of static that accompany solar flares. Together, these ground-based watchers provide the context, the Earth's response to storms that begin upon the sun. All of this effort converges in centers like the NOAA Space Weather Prediction Center in the United States and its counterparts in Europe and Asia. These institutions serve as the world's storm sentinels, issuing alerts and forecasts to power grid operators, satellite controllers, and aviation authorities. Their task is formidable: to predict storms born upon a star whose physics remains only partly understood. At best, they can provide hours of warning, enough time, perhaps, to reconfigure satellites, reroute flights, or protect power grids from overload. But unlike hurricanes, which unfold slowly across oceans, solar storms can erupt with little notice, racing across the void in less than a day. The challenge is constant: to see further, earlier, more clearly into the sun's hidden tempests. The fragility of modern systems ensures the stakes are high. Power grids, sprawling across continents, act like giant antennas, vulnerable to currents induced by geomagnetic storms. Satellites, the silent architects of GPS, communication, and weather forecasting, can be blinded or crippled by charged particles. Even undersea cables, carrying the internet's invisible lifeblood, could suffer induced currents strong enough to melt their components. The more deeply humanity entwines itself with electricity, the more exposed it becomes to the sun. Thus, science does not study the sun in detachment. It studies in defense. The Carrington Event remains the cautionary tale, the specter that haunts every forecast, the precedent that keeps engineers awake at night. Each new mission, each new model is not only a step toward knowledge, but a shield raised against the fire. And yet, for all the progress, a sobering truth remains. Our tools can watch, measure, and warn, but they cannot prevent. The sun is too vast, its storms too immense. The best humanity can do is anticipate, prepare, endure. The Carrington Event is a reminder, not only of vulnerability, but of humility. For all our satellites, our probes, our forecasts, we remain tethered to a star that does not ask our permission when it decides to storm. The watchers in orbit and the observatories on Earth form only one half of the defense. The other half lies in preparation, in imagining what the next Carrington Event might do, and in rehearsing responses before the storm arrives. For in the age of electricity, foreknowledge is not enough. It must be coupled with resilience, with a capacity to endure the inevitable. Across the globe, governments and scientific agencies now conduct preparedness drills for solar storms. These are not abstract exercises, but sobering rehearsals of disruption. Power grid operators simulate what might happen if transformers, vast machines at the heart of electrical networks, were to overload under geomagnetically induced currents. Scenarios envision blackouts stretching across entire regions, cascading failures that could silence cities for weeks. Plans are drawn for rerouting power, for isolating vulnerable systems, for replacing critical components under emergency conditions. Satellites, too, are tested in imagination. Agencies consider how to place spacecraft into protective modes, shutting down sensitive instruments to ride out particle bombardments. Air traffic controllers rehearse rerouting polar flights, where radiation exposure can spike during storms. Even undersea internet cables are studied for vulnerability, their repeaters and amplifiers examined for resilience against induced currents. Each exercise, each model, carries the shadow of 1859, a reminder of the last time the sun showed its teeth. No single nation shoulders this alone. Space weather knows no borders. The European Space Agency runs its own Space Weather Coordination Center, pooling data from across the continent. Japan's JAXA contributes with missions like Hinode, probing the sun's magnetic knots. India has launched Aditya L1, its first dedicated solar observatory, to watch the star from the same Lagrange point as Soho. Together, these efforts weave a global net of vigilance. For the sun is not the concern of one nation, but of all humanity. And yet, despite the fleet of satellites, the drills, the centers issuing forecasts, uncertainty remains. A storm like Carrington's fast, immense, ferocious, would allow little time. Warnings might come only hours before impact. The power to prepare would be constrained, decisions forced in haste. Our systems are complex, interwoven, fragile. No model can predict how a global blackout might unfold, how financial systems, hospitals, transportation, and communications might falter in concert. The very complexity of modern life is itself a vulnerability. Engineers work to harden the grid. Transformers can be built with greater tolerance. Grounding systems improve to bleed off geomagnetically induced currents. Satellites are designed with shielding, circuits tested against radiation. Airlines train. For many scientists, this reality carries a philosophical weight. The Carrington Event, retold in journals and warnings, is not just a precedent, but a parable. It reminds us that human progress, our grids, our networks, our satellites, our endless currents of data, rests upon foundations that the sun can shake. The same star that painted the auroras in September 1859 still burns above us, restless, unpredictable, waiting. Our tools have grown, but our position has not changed. We are children of the sun, dependent upon its light, vulnerable to its fire. The next great storm will test more than infrastructure. It will test resilience, cooperation, the ability of nations to face a challenge that respects no border. It will test humility, the recognition that, for all our science, we remain at the mercy of a star. Preparedness drills and forecasting centers are acts of prudence, but beneath them lies an admission. There is no absolute safety. There is only vigilance, only readiness, only the hope that when the sun stirs again, we will meet its storm with eyes open. And so the work continues. Satellites stream data, observatories keep watch, supercomputers churn through simulations, agencies trade warnings across oceans, rehearsing for a night when dawn may not come. The story of 1859 lives on, not as history, but as prophecy, a reminder that the day the sun almost killed us may come again, and that only through science, preparation, and humility can we hope to face it. Night after night, the skies above Earth appear calm. Stars glitter in their silence, the moon drifts across its orbit, and the sun, though hidden, promises to return at dawn. For most of humanity, the heavens have always been symbols of constancy. They rise, they set, they repeat. And yet, hidden within that repetition lies turbulence, a truth glimpsed only rarely in moments like September of 1859, when the sun pulled back its veil and revealed its dual face. To remember the Carrington Event is to remember how fragile the illusion of stability can be. The men and women of the 19th century lived in a world almost untouched by electricity. Their lamps burned oil and gas, their ships caught the wind, their fields depended on the soil and the rain. Only the telegraph carried the pulse of current across wires, a new invention, tenuous, miraculous, and still, the storm shook them. Sparks leapt, fires flared, auroras blazed where no aurora had ever been. For them, it was enough to inspire awe and fear. For us, it carries a far deeper warning. For now, we live in a world spun entirely from electricity. Invisible threads of power hum beneath every city, beneath every street, linking homes and industries, hospitals and markets. Satellites orbit above, guiding planes, synchronizing banks, mapping oceans, and connecting voices. Undersea cables knit continents together in webs of light. The pulse of modern civilization is no longer the hoofbeat of horses or the whistle of steam, but the steady rhythm of electrons coursing through fragile veins. Imagine, then, what the storm of 1859 would mean if it came tomorrow. The auroras would return, yes, painting the skies with blood-red and emerald fire, dazzling crowds who would lift their phones to record them until their phones failed. But beneath the spectacle, transformers would begin to overload. Satellites would fall silent, their circuits fried by invisible particles. Aircraft would lose navigation. Internet cables could suffer damage at depths where no human hand can reach. Cities might darken, not for hours, but for weeks. Commerce, communication, the very fabric of order, all vulnerable to the same force that once made telegraph wires spark in the night. The reflection is sobering, for in the 19th century, the storm was a spectacle. In the 21st, it would be an existential test. the same star that gives us life, could, in an instant, strip away the systems that sustain our civilization. The Carrington Event is therefore not just history, it is prophecy. But within this prophecy lies a deeper philosophical question. What is humanity's place in a universe so volatile, so indifferent? We have long imagined ourselves masters of progress, building machines to tame nature, engines to conquer distance, networks to span the globe. And yet the sun reminds us that mastery is temporary. We are not above nature, we are within it. The same light that nourishes our crops, that drives our seasons, that makes our days possible, is the same light that carries storms across the void. We are dependent, utterly, upon a balance we cannot control. To contemplate this is to feel both humility and awe. Humility, because our greatest achievements, satellites in orbit, grids stretching across continents, invisible clouds of data, are fragile before the breath of the sun. Awe, because we live within a universe that is alive, dynamic, restless. The sun is not a lamp burning quietly in the sky. It is a furnace of storms, a churning sea of plasma, a star among billions, yet uniquely ours. Its rage and its generosity define the story of life. In this duality, the Carrington Event becomes a mirror. It shows us the precariousness of our existence, but also the wonder of our survival. We have endured its fire once, and we will endure again. Science arms us with tools, with forecasts, with shields of knowledge. But philosophy arms us with something deeper, the recognition that fragility is not weakness, but part of what it means to be alive beneath a star. The story of 1859, then, is not only about danger, it is about perspective. For if the sun can, in one night, paint the skies of Cuba and Rome with auroras, set telegraphs ablaze, and still rise the next morning to feed the earth with warmth, then perhaps we glimpse the truth, that creation and destruction are not opposites, but partners. That to live under the sun is to live in both light and storm. And so the question lingers. Not whether the storm will come again, for science suggests it must, but how we will face it when it does. With fear? With awe? With preparation? Or with the same wonder that Carrington felt when he sketched the flare, unaware that he was witnessing a warning written in fire? The clock is ticking in the heart of the sun. Each rotation, each cycle of spots, each flare is another reminder. The day will come when the storm returns, and when it does, the story of 1859 will no longer be history. It will be the present. The story of the Carrington Event closes not with certainty, but with silence. The silence of a mystery unsolved, of a question left suspended in the sky above us. The sun continues to burn, indifferent to our fears, indifferent to our prayers, indifferent even to our science. And yet, in its silence, it speaks. Each aurora, each flicker of magnetic disturbance, each flare captured by a telescope, is a reminder that we live not apart from the universe, but inside its breathing. For the people of 1859, the storm was a miracle and a terror. Miners in the Rocky Mountains awoke at midnight, convinced that dawn had come. Families in Havana stood in streets washed red by auroras, whispering of omens and divine fire. Telegraph operators recoiled as sparks leapt from their instruments. Some saw beauty, others saw judgment. None saw the science that would later unfold. To them, it was a cosmic visitation, unexplained, unforgettable. For us, it is something more. It is a lesson in scale, in fragility, in perspective. Our entire civilization rests upon thin layers of technology, satellites orbiting in fragile shells, grids of wires stretched across landscapes, pulses of code leaping invisibly beneath oceans. We imagine these systems permanent, as though the internet and electricity were as natural as rivers or mountains. But the sun reminds us, they are not. They are inventions balanced upon foundations that a storm can shake. The Carrington Event is not only a memory of what the sun once did, it is a forecast of what it will do again. And here lies the deepest reflection. The sun does not act with malice. Its storms are not punishment, nor warning, nor sign. They are simply part of its nature, the physics of a star whose heart churns with fusion, whose surface writhes with magnetic fire. To live beneath it is to live within its moods. The question is not whether we can control the sun. We cannot, but whether we can accept our place beneath it. In this acceptance lies a kind of philosophy. To recognize the sun's duality is to recognize the paradox of existence itself. Life is born from fire, yet fire can unmake life. The same forces that nurture also threaten. Creation and destruction are woven together, inseparable. The Carrington Event is a reminder that safety is never absolute, that certainty is an illusion, that even the most constant star hides storms within its brilliance. And yet, within this fragility, there is also resilience. Humanity has endured comets, plagues, earthquakes, wars, and still it endures. The sun may one day unleash another storm as fierce as Carrington's, and perhaps stronger still. It may test our grids, our satellites, our networks, but it will not extinguish us. It will instead remind us to adapt, to prepare, to live with humility beneath forces larger than ourselves. So the story does not end in fear, but in perspective. When we look back to 1859, we see not only sparks and telegraphs and lights in the sky, we see the first time humanity glimpsed the truth of its environment, that space is not empty, but alive, that the sun is not constant, but restless, that we are not isolated, but connected to the storms of the cosmos. And when we look forward, we do so with both awe and caution. Awe, because we live beneath a star that paints our skies with auroras, that feeds our world with warmth, that powers the miracle of life. Caution, because that same star carries within it the power to humble us, to remind us of limits, to strike our fragile systems with fire from across the void. The Carrington Event is thus more than a historical episode. It is a parable for the future, a narrative etched in plasma and light. It whispers that progress is not immunity, that connection is not invulnerability, that every advance carries its own vulnerability. It whispers, too, that the sun, eternal in our myths, stable in our calendars, is in truth a storm waiting to break. And